So I'd now like to introduce our opening keynote speaker, Pieter de Wilde. If you've not heard of Pieter, you're probably pretty new to the community. And for many of us who have been around for a while, he's certainly one of Building Performance's big hitters. Pieter will be speaking to us today on AI in building performance simulation, a topic which I'm really excited to learn a few things on. So please join me in welcoming Pieter to the stage.
Thank you, Nikki, and thank you for the introduction. And I'm very pleased to be here today and do this keynote on what is quite a hot topic. Let me see that I get this going. Yeah. So AI is really in everybody's mind at the moment. There's a lot of stuff happening. It also makes it a very challenging topic to deliver a keynote on, because I need to keep in mind that some of you will be relatively new to this thing and maybe need almost a primer on the subject. And we have other people, and I've seen talks already in the conference, that are really at the forefront of what is happening here and are helping to develop the tools and bringing this into building simulation. So that is a big job that I have here today. This thing is not, it responds a bit slowly, sorry. I need to go back, there we go. So why am I talking on this topic, and what is my, it goes back and forth. I'm not sure, that is the one I want, and let's be careful with this thing and just put it away. Okay, so why am I talking on this topic, and what is my credential here? I've been working with some of the stuff that fits in the AI banner for a long time. I've been doing work with genetic algorithms, support vector machines. 15 years ago, I've been playing with meta models to speed up our uncertainty analysis work when we did a project in the same area. But I've also been involved in another group, and that is something that the IBIPSA community probably is not very aware of. There's a small group in Europe, the European Group for Intelligent Computing and Engineering, that does a lot of AI work. I've been deep into that group, and on the back of that, I became associate editor of a journal called Advanced Engineering Informatics. And that journal started in the mid-80s as basically AI in engineering. So a lot of the content that comes through that journal hits this topic, and that is why I think I'm certified to talk a little bit about these things. But you give me the verdict afterwards. What I'm going to do is, like I said, start from the basic and build up. So some of you do not know a lot about the subject, so I need to kind of start with an introduction 101 and then move on to what this means for BPS, for building simulation, and what we can do with this technology. I will also reflect on a few projects that we have in LTH where I work and kind of see how this technology fit in what we're just starting over there. I'll end up with the built environment, because that also has a role with AI, and that is a bit of a warning at the back end point, and hopefully end up with some take-home points that will give you something to think about what you do in the next couple of years. So one of the things is this role of associate editor is that I kind of play something called AI word bingo. This is the terms that come over my desk almost on a daily basis. And some you might recognize, and some you think, what the hell is this, and what do we do with it? Yeah, and it is a very quick, growing field, and you need to stay on top of these things, and that is what makes it challenging. So rather than start to explain this, because this is too much, I start very basic. Yeah, so what is AI? AI is basically computational systems that do work that we typically assume that human people do, and that is learning, reasoning, deciding. That is what we try the computer to do. Then within that, we can discern two types of AI. Weak AI is where there's a very specific task, and we can train the computer, and the computer gets incredibly good at doing those things. Yeah, so for instance, think about a computer playing chess. The computer can beat the world champion in chess because it's well thought, well structured, and it's very strong in that direction. Then we have strong AI, and that is on the horizon at the moment. People are worrying about it and talking about it, but that is where the computer becomes really at the human level cognition, but that's something else, right? That is doing all different tasks and combining that together. A different thing which you see is machine learning, and that is a subcategory of AI, and that is basically statistical algorithms that learn from data rather than us giving them explicit instructions. If we contrast that to building performance simulation, and I put the definition up there, coming from the book from Jan Hensen and Roberto Lamberts, the replication, prediction of aspects of building performance using a computer-based mathematical model and applying fundamental physics and engineering models, that's what we do there. That kind of overlaps, right? And especially within BPS, for many years we already talked about glass models, white box models, where we explicitly define functions like heat transfer. We build that into our tools. But you can also use a black box. Then there is a relation between data and we don't know exactly what it is. But you can put that in a BPS simulation. So then we already have machine learning basically embedded in BPS. Another thing to get your head around is the history of AI. So it sometimes feels like this is new and this is a trend that comes out of nowhere. But AI has been around for a very long time. It goes back to just behind the Second World War, thinking about how we make computers that think. And from there what we had is a number of AI springs followed by AI winters. You see on the graph how that develops, and at the moment the question is, are we at the breakthrough or are we at one point coming to the conclusion that the technology we are developing now also is not completely doing everything, and do we end up with a third winter? We don't know. We're at this point there where the consensus is basically located. Interesting also to see that this kind of even precedes what IBIPSA has been doing, right? So this goes back to the 1950s. Our first algorithms are from the 1960s, so it's been around for a long time. If we stick with the high-level overview, then AI, from the inception, covered a number of things that when people start, okay, can we make a computer think? We were doing a number of things that we're actually still doing today. So one thing is dealing with natural language. NLP, natural language processing, machine learning, but also feeding computers images and having the computers process images, so computer vision, working with construct accepts and reasoning, and creativity. That's been around, and we're actually still doing that. Next couple of slides give some of the overviews of how people at the moment see AI. And it's interesting to go on the internet and find these images and start to reflect on them, and you see kind of different categories. So this is kind of models that stick with this original worldview of what people were doing, and you can kind of plot that in different ways and give different names to it. But the big breakthrough here is this machine learning, which is on the top graph on the right. You can see that on the left there, the little box. That is what's really exploding at the moment. But here's another worldview, and it starts with artificial intelligence, then it goes into machine learning, it goes into, I need to put this off, the neural networks, and you can go deeper and deeper and kind of has this concentric view that we go deeper and deeper in one area. But you also need to step back and say, well, these other fields are also developing. The machine learning is really the bit that is on the front end, and there's also different depictions of that. I talk a little bit later on what it is, but there's three main categories in machine learning, and it kind of has this tendency to keep growing, and you see this from the two diagrams on the screen. I almost call it the Mandelbrot. You start knowing what the three branches is, and then within each branch there's other sub-branches branching off, and then more little tentacles coming out, and this keeps growing. That also makes it difficult to stay on top of everything that's happening. But just as the 101, as the primer, let's quickly go back to the three main categories of machine learning that are around. The first is unsupervised learning, and what you basically do is you give the computer data and you let it cluster, find patterns, regularities that we as a human being may not be able to do, right? You can give the computer multidimensional data, a lot of it, and it will find you clusters and do fantastic things for you. The second thing is supervised learning, and basically what we do here, we feed the computer with data that we label, so that's why the supervision comes in, and then we train the computer to recognize things, and then it's able to categorize new information that it has not seen before. And the classic example is you show a computer a lot of images of cats and dogs that have a label cat or dog, and then you show it another image, and then the computer is actually pretty good at predicting whether it's a cat or a dog. Problem is if you bring something in that the computer has not seen before, right? So you train the cats on dogs and you show it a bird, then it has a problem. The third thing is reinforcement learning, and that is where computers are given a task, like to predict something, and if it's got the prediction right, we like that, and we kind of give it credits for getting in that direction, and we sterken the algorithm, we say this is a good way of doing. If it's got it wrong, we give it a penalty, and it kind of starts deviating from that thing. So those are the three main things that we do within machine learning. Few further words, that's just to make sure you can talk about these things and you know what is what. So neural networks, it's basically one of the ways we do the training based on what the human brain does with neurons and connections. We have an input layer, we have an output layer, some mass in between, and if we feed data on the input and we know what the output is, the middle layer kind of defines how the connection is. Deep learning, the same story, but more layers in between, so we can deal with more complex patterns and more complex data. Transfer learning, that is where we take something which is trained for one thing and we slightly tweak it to what we think is an application that is close enough, but of course with some risk doing that. We talk about hyperparameter tuning, and it's basically messing with the concept of the neural network with some of the parameters in there without addressing the data. It's just the background of the calculation. And by tweaking that, we can sometimes get better results. And ablation studies, that is where we have machine learning approaches and we start to turn off elements of the prediction one by one to kind of see what the impact is and learn a little bit more of what the performance of the model is. The other thing you will see a lot, and we've seen a little bit of this in some of the presentations already, LLM, LVM, and LRM. So large language models, large visual models, and large reasoning models. And I'm sure there will be more to come along this paradigm. Basically, we go back to dealing with language, and now we make models that are trained on vast amount of data. And what we like to do is actually use the whole internet and everything that's ever published and stick that in a model. So obviously, that is an enormous training set. In the background, we take words and letters and we convert them into numbers and into vectors, and then we apply statistics. And if you know the first three letters of the word, the computer can predict what the rest of the word is. If you know two words of a sentence, you can start elaborating on that. And it's amazing what you can do. That is what basically ChatGPT does in the background. Yeah? And that technology that sits in the background, we call the transformer backbones, or sometimes foundation models. They might have something in there which is an attention mechanism, and that is while you work with it, you can interact with it, and you can kind of steer it in the direction that your interest has, so you can kind of refine your queries. We can do that with language. We can also do it with images. Yeah? Large visual models, same technology, same transformer backbone in the background, but now we deal with images, segments, pixelated, and we can start doing the same thing. And we're now at the moment moving into reasoning and trying to get logic in there and actually, again, train computers statistically to recognize the logic and work on that. A few other things that you might just have in the background, just to make sure that your overview of all the digital stuff that goes on is there. So we've got digital twins, basically a real thing like a building, a computer model, and it communicates two-way. And of course, you can insert AI there. And depending on how you push the information forwards and backward, it might be a real digital twin where there's two-way communication that is fully automated, or it might be something manual, then we call it a digital model, or a digital shadow where there is one-way automation and the other way is less automated. Cyber-physical systems, what is the difference here? Very close, but here we have basically something like a robot arm where the intelligence sits in the computer, might be the AI, and it's essential for that system to have the computer brain to operate. And just to be complete, Internet of Things is basically sensors everywhere that talk to each other and connect via the internet, and of course then also can feed data into AI, and our good old trusted building information models that we talk, for instance, about in our workshop tomorrow from the Annex 91, and you're welcome to join that one. So that is basically a primer of what AI is and what it does, so AI 101. But I also wanted to touch on some of the debate in here. So you think about this technology, And there's great advantages and opportunities in here and reasons to embrace it, but there's also concerns in there. If we start with the opportunities, so this technology does amazing things. You feed statistics, you have this technology predict things, it can write text, it can search the whole database, what we've produced on the internet with our human knowledge, can do that very fast, can be cost saving, can do things a million times faster than we can do it as humans. It is automated, so less error, better decision making, convenience, innovation, wonderful things, and we need to embrace this, right? So that's the one side of the thing. There's also concerns. On the concern side, the first thing is something called the singularity, and that is where the point arrives where we have this strong AI, where the computer becomes smarter than the human brain, and people are concerned about that. It's a question how we deal with that and how close we are. There's some people that say that we're within years, there's other people that say it's decades away, but it's a point to think about, right? If we build machines that think so very clever, is that a good thing? Alignment problem, that's something that we really need to think hard about. We train a computer on data, and it does amazing things, but does it really do what we want to do? Or are we building in biases and does it have unintended consequences? And this morning there was the breakfast session on ADI, alignment problem. So you train a computer to process language and we let it fill in the prompt, right? And you feed it with a couple of words and you let it fill out the next word. And you give it medical job male and it gives you doctor. You give it medical job female and it gives you nurse. There's a bias in there. But that's what all the text that is on the internet over the years has been saying. So we need to be very careful whether that data that we feed in, whether that actually has something in the background that might not be what we want. And if you start thinking about our field, we also need to look at what we do there. AI causing job displacement. So as a professor, am I going to be replaced by a computer that actually does the tutoring for the students? We need to think about that. Potential for misuse, politicians and other people that do things with AI that maybe we do not want to happen. Accountability, privacy, so there's all kinds of things in there that we need to think about. A final one to think about is this pyramid that people often show where there's this natural progression from you start with data, you process data, from the data you distill information, from information you distill knowledge, and on top of that you get to wisdom. This whole idea of applying all this technology, does it really lead to wisdom or do we just stay at the bottom layer and deal with data? We need to think about whether this is really what is happening and whether we're getting to wisdom or whether we're just automating stuff. Okay, now I'm going to switch to how all of this fits in building performance simulation. And the first thing that I did, and you can look at the screen and read out what is there, but of course the first thing I do is ask ChatGPT itself what it thinks that AI will do for building performance simulation. So I give it a prompt, what can we expect from AI on building performance simulation? And it comes up with a quite good response. The first time you think this, wow. Yeah, so it starts saying that, okay, AI is going to change the world of what we're doing, and it's going to do a couple of things. It's going to allow us to do faster and smarter design decisions. It's allowing us to enhance model calibration. It's going to give real-time operational feedback. It's going to help us do more of the urban and the portfolio simulation, so scale up the activities. And it even is so good to say in the final point that there's challenges and limitations, that for instance this import from BIM to BEM is one of the things that is not working perfectly and that we need to pay attention to that. So that is, wow, the computer can tell me that based on that simple prompt. But then if you go reflecting on it a little bit, it's also what we've been saying at these conferences, but also the things that we know we talk to each other about, but there's dangers in here, right? So this myth of better design, I've been spending my whole career on that, and simulation is great and it helps design, but how much the speed in there and whether it really gets better decisions, it's open for me. If we talk about calibration, yes, it can do things. I've seen some very interesting work in that area. The operational feedback. Anybody who's ever done fault detection and diagnosis knows that that is very tricky. You have the problem of discerning your noise and your signal and finding out what's really happening. So there's deeper caveats in here, and whether AI is the solution, I don't know. I also go back to the journal and I show you what is going on the front end on a lot of simulation stuff. And I probably need to talk to Ian Bosolai about whether they get the same thing as type of submissions. But this is what I see in a lot of work that crosses my desk. And you will recognize it, right? So the first sentence or alinea is about some grand problem like climate change or dealing with heat waves or medical problems. And then we say, okay, we're going to solve that by doing something with AI. We pick up an algorithm and you can go from the word bingo or one of the little branches of the Mandelbrot graph and you pick something, that is what you're going to play with. Then you throw in a good bag of technical terms that are related with that. So feature extraction, segmentation, data fusion, something of that kind of makes it even more complex. Then we do some experiments and we claim an extreme accuracy, so something like 99%. We say, okay, that is another 5% higher than what the state of the art is. Great work, we are having a step change in this domain, right? But if I look at this, I think this is weak AI. This is one direction, it's one algorithm, one small problem that we're dealing. It's not this strong AI where we're really making a difference on that thing. So I reflect on it and I think I see a lot of this. This is what people are doing. And the strong AI, I think, is a different game. I also reflected on what it is that we do as building performance simulation scientists, engineers in the daily practice, and how that fits to some of those categories that we had, right? So the broad things like pattern recognition, need to get this off sometimes, classification, optimization, handling the big data, natural language, generative AI, that's the things that sit in the area that you want to do. Reflect on what it is we do as building simulation people. Typically the first thing is client interaction. Talk to a person that wants to build a building or convert a building. Problem definition, deciding what tool to use. Then within that tool, develop your model or select a pre-existing model. Start to import your geometry and get that right. Find your material properties, define your building surfaces and how that works in that model that you have in there. Play around with occupant behavior and control settings. That's going to be quite a challenge. Select your weather data. Do we use past data, future weather? Do we use extreme conditions? Look at what you want out of the model. What performance metrics do you want to have? If I use the word I don't like to use, but KPIs in the back end. Then you run your simulation, you go back to the result, you check them, verify, validate, calibrate, you do your optimization and your search, you analyze, you aggregate, you report, and then you communicate back to the client and hopefully you learn something for your future events, right? If I then look at those main categories, there's some mapping between there, but there's other areas where I think we're not doing that yet and we're not even getting closer. Trends in building performance simulation. So I come from the other end. So what are we doing and talking about in this conference? Well, hard to give the overall view, but what I did is I looked at the JBPS, or IBIPSA journal, the viewpoint articles in there. That's kind of an indication of what people are doing. There's also the Springer journal that has perspective papers, looked at them. Even building an environment and question papers. And I looked at the last 3 conferences. And then you come up with a list. And some of that is straight on AI, right? So new computational approaches, AI, machine learning, large language models, that's one of the things that pops up here and that people are interested in. But there's other things that have nothing to do with AI, like what is sustainability? How do we handle indoor air quality and indoor environmental quality? Commissioning, policy and energy codes, stuff that goes in a different direction and we have different expectations. So we need to map those two. Where does it start mapping? Well, I see, and that's where I said I've been involved in this game for a while, meta and surrogate models, where we actually use AI to speed up the simulation. We've done that for a long time, and that is I think, accepted work in our field that we do a lot. Design exploration, using AI to search a space, to look different parameter combinations. That's something that we really do. The larger scale things, the high level aggregation, can't run simulation for all the buildings in in a city, so you use AI to kind of reproduce models and do that thing. The digital twins have benefit here. Data-driven models in themselves are by definition in that category. In the control area, we see a lot of AI actually, where actually putting something in a little box that controls your window or your ventilation system. That is where this stuff is in there. And education, e-learning is coming up. New ways of tutoring online, computers do that well. So that is where we are in there. But we also need to look at where the challenges are. And I always think that one of the real complex things in building simulations is the complexity of buildings. I've been for my whole career trying to understand buildings, and I'm even as a full professor, I'm still amazed of all the variation and the combinations and how difficult that is. And then we've got scalability and aggregatability. That's another one. My professor at Georgia Tech, Fried Augenbrew, always said performance doesn't scale. So yeah, I'm not sure how that implies for what we're doing with AI here. The uncertainties and the risks is difficult to do. Multi-domain, combining how one simulation impacts on the other. It is already complex, but the whole combination of ventilation, lighting, acoustics, how it all interacts is a difficult one. We still grapple with energy performance gap, so I have a PhD student and they will talk later today on that. But our predictions are not that good. So if our full engineering-based prediction is not good, how is the AI that we train from that? And in the back end, you know, we want real-world impact, and it's even a logo of the a slogan of the conference here. But it's always been the difficult one where we believe in simulation in this room, but if you go out to the people that make decisions and invest the money, it is a hard sell. I also wanted to flag up the 7 deadly sins of building performance simulation. And remember Professor Joe Clark from Strathclyde, and before him Ton Maver 15 years ago, they had this 7 sins of simulation. And I think we should look at these, and if we talk about AI, see how that maps. First one was macromyopia, and that is kind of where we design systems and we think it's all singing and dancing, but they always question that. I think we should in 15 years, in 35, go back to this and see what AI has done and whether it is all singing and dancing or not. Deja vu and amnesia, where we did stuff in the past, it didn't work, we forget about it, 15 years later, a new generation tries it again. We've been there with simulation tools that are supposed to be quick design support, right? Now AI is claiming quick design support. Will that work? Didn't work 15 years ago, so where are we with that? Third one, very interesting, xenophilia, where we love what happens in other domains and bring it into building simulation. And we love to look at computing, and we love to look at systems engineering, and now we like to look at AI and see whether we can bring it in. But we need to be careful there, we need to check what happens. Non-sustainability, overindulgent developments, where we make something that is great and grand, and then we don't have the resources to back it up. And the 3 at the back we don't need to talk about, but failure to validate, evaluate, criticize. So some of the young people in the room, please take note of the 7 deadly sins, and in 35 we need to come back to this. Okay, now on a more positive note, where are these things going? And I was kind of searching for this keynote for some overview that goes from the complex to what is happening and to basically what's the frontier. And what I found was this graph from the Japanese Society for Artificial Intelligence. And I really like this graph because it kind of shows different groupings of overall things that we do. So from the knowledge and the reasoning that's in the back, discovery and search and creation, that is what we do when we create buildings. Evolution, life and growth, things that develop in the right direction. Things about human interaction, how we connect with people in different ways. Body, robots, motion, that is actually systems. Buildings as a robot was something I heard in one of the presentations, so this resonates with me. And it shows on the outer core some of the fields that are being drawn into AI, and there's many. And then at the front end you have this AI with things like the singularity and in there. So I took that graph and I kind of converted that to where our building performance simulation with AI frontier might be. And what's on the outline is exactly the same as in the previous one, so I took that across. I put some of the other terms in blue. I think that is fields that kind of help what we're doing and support where we're going. So we link with data science, we link with engineering, with genetic programming, all that type of thing on there along those lines. The black words come from the previous graph, so that is stuff that happens in the wider world and that we can apply to our thing. And I added the red ones as areas where I think this is stuff that what we are doing right now is where that might fit and where we actually could help what we're doing. Yeah. And if I go a little bit from the top, for instance, if we make models, searching the data that goes in these models, I think AI is great for doing that. Finding all that information hidden in the internet that's everywhere, we could really use that. Data augmentation, so you have missing data points, how do you fill that in? AI great at that, doing that stuff. Evolution, well, we've got kinetic algorithms and we can have instant feedback, so maybe that helps and we should explore what happens in there. Design decisions we could support, but reporting, you know, I'm always frustrated with the simple report that comes out of Energy Plus. I'm sure AI can write much better text, much better reports, and we can use that. Key performance indicators, if you want to use the term, although I personally prefer performance measures. We can build a co-pilot where actually the AI technology will suggest how we proceed doing our simulations and kind of help us customize the menu while we do our work. Something that we really can start building. On dealing with robotics, well, of course, smart control, autonomous systems, the digital twins is something that we can push. And in the learning side, I think especially the validation and the verification is high potential. I also like to pull this graph. This is something that I've developed on the back of my book, which appeared in 2018. But this reflects on the fact that we have so many performance aspects. We tend in this conference, in my view, always to talk too much about energy. But there's all these other aspects. So there's a little bit of lighting, a little bit of ventilation. Sometimes people talk about money and acoustics. But in my view, there's around 80 things that buildings need to do well. And some of them we simulate, but others we do not. And my bugbear example is burglary protection. You can test it in the lab, but we cannot simulate it. Yeah, let's use AI to see whether we can make a tool, maybe a black box tool that kind of predicts those things and kind of gives some background to what we're doing and transfer lab information to your engineering positions. So that is stuff where I think we can be heading. I'm now going to reflect on some stuff that we do in our university, LTH in Lund. This is work of dissertation students from this year, and they were looking at their lab facility. That's a real building with test cells in there. And they were on their way to try to make a digital twin of that. You go look at existing data. These guys, even without me telling them, to fill out missing data, they start relying on AI to fill in the gaps. To get the calibration right, automatically they go to these machine learning programs and do that stuff. So it is coming even at the MSc level, even if your professor is not even pointing you in that direction. And the stuff that comes out there is very, very striking, right? So these are two test cells, 108 and 109. That's actually room numbers in the lab. You have a prediction performance gap on the bar on the left. Then once we have a measured situation, you get a better data, you get closer up. But when you apply the machine learning, it almost disappears on the right-hand side, the search sets of bars. Yeah? So really, really coming and not to be ignored. But at the PhD level, there's also stuff that we do that I think, if I reflect on AI and what it can do, we have a long way to go. We have one student starting just a couple of months ago on this BIM to BEM conversion. And one of the things we find that there's many pathways, and we don't know which pathways are the right one. There's data pipelines, and we kind of took the analogy with a metro system. But you go from one actor to another actor, different ways. Do you go IFC? Do you go GBXML? What tool do you use? How do you navigate that pathway? I do not know yet. We need to find that out, and it's a difficult one. My other PhD, who just started weeks ago, she's going to work on the interface between sustainability and fire safety engineering. And the key thing that we always do is pull up a fire of the Grenfell Tower. Yeah? There's a building that was retrofitted to make it more energy efficient. Then there was a fire and people died because of the insulation material on the panels. Do we want to hand this over to AI? Whose responsibility? What are the ethics in here? I think this is a clear area where we think we need to be careful with what we're doing. And we need to make sure that if we give this to a computer, we want to be accountable and know what's happening. Yeah, so it shows what is in there. The elephant in the room, I'm coming towards the end of the talk, but this is a building, right? This is a data center. This is what runs AI in the background. And this is one in the Netherlands where I come from, a data center in Middenmeer near the airport. Small problem here. Current data centers use as much energy as a small city. We have AI wanting more and more and more data, more and more processing. So we're moving from data centers to data campuses. And you know where they built them? Close to previous fossil-fueled power plants, so we have a nice backup system to actually drive this system. Or a nuclear plant so we can run it. So we need to start thinking about how much energy goes into running the AI. And that is one thing that we as a building community should be looking at. And I was very happy this morning to see a poster that was dealing with that subject. But we need to do more on that. As the energy use of the big tech is estimated to grow 5 to 15 times over that next period of 20 or 15 years. At the moment, 1.5 of global greenhouse gas emissions is already due to AI, and we have a growth of 15 to 30% per year. So we try to make buildings a little bit more efficient, and then we use AI to do that, and that just goes through the roof as this exponential growth goes, yeah? So we need to work on that. So my take-home points, and it's good, I've heard this already when I talk about this subject, people say, we need to look at this, it's going to change our job. Yes, it is. BPS is going to change because of AI. And I think that's going to really impact some of the tasks we do, whether it's writing reports or teaching students, this technology is going to change. It's great for, I think, the weak AI. Specific tasks where we have algorithms, we can control them, we can measure what they do. I think there's a lot of opportunity in there. This journal that I reviewed for, we have this year 6,500 submissions so far, so it shows the interest in there, and I think we'll make good progress in there. But we need high quality trusted data, and that is challenging. Yeah? I've always, if you try to get data from another group to help do your own simulations, I'm not sure it is confidential. So getting that trusted data out there is a real job. And if we want to trust AI, we need to trust how it's trained. We need to know how that data that goes in there, that we can actually be confident in that. So that is a real challenge. Another point I would like to make, and that is the traditional white box models, the engineering ones, we should not throw them away, because that is our formalized domain knowledge. That is how we started predicting things. That's how we train students. And if I look at data, I always like to do the quick calculation and see where the ballpark is right. Yeah, so we need to keep those models. AI will come, but we should not only go AI. We should keep being critical and understanding what the system is doing. Buildings are really complex, and I mentioned that before. And I think that one of the things that building simulation does, and I remember at one conference they talked about building simulation not being a science, but also being partly an art, right? It's abstraction. It is taking the complexity of the world, saying we're only looking at, let's say, energy. We zone things into groups, so we don't model all 500 rooms in the hotel, but we kind of multiply and we do it in a smart way. AI is not good at that, and we need to keep doing that stuff and making sure that we know what's happening there. But there's also, to be on top of AI, we need to have awareness of what this technology does, how it works, where it applies, what the assumptions are, and also what the limitations are. So with that, I think I have only 2 minutes for questions, but I'll end the presentation here and give the word back to the chair. Thank you.
So my question is something that has always troubled me with AI, and that's around the ethics of where the data comes from. And but I'm not an expert in any way, so I'm just curious about all the data that is used to, I know this is kind of separate from simulation, but I feel like thinking about the ethics of where our information comes from is important.
Yeah.
Yeah, I'm just curious because I know that we've been trying to do some AI stuff at work, and they keep saying, oh, it's okay, you can put in your own data for it, but where is it getting, I guess, I hear this mostly with respect to like ChatGPT and things like that, like stealing, authors and
Yeah.
What about like when it comes to simulation, like where is that information coming from? Is it ethical? Is it like, not just the bias part of it, but how is it being sourced?
Very, very fair question. And I think the large models, if you go out and use the whole internet as a source, it's probably partly unethical. Yes, I agree with that. But then on top of that, there's the question of how biased might that information be. So I can take internet data to say, I need to kind of have the standard comfort conditions and source that from throwing it at the world. But there's different areas in the world, different expectations. It's a very high chance that my answer is biased by work that's done in the past, so thermal comfort. Basically for the American business male in the costume in his office, does that apply to somebody who is in some republic where there's little money and no... I don't know. That is a question that we need to ask ourselves. And so... The question about the ethics and the quality, I think, is hand in hand. If we just go out and say, well, ChatGPT, give me this profile, I'd be not comfortable with that without double checking and seeing where it comes from. Yeah. Good point.
Hi, thank you for the presentation here, Veronica. I'll stand up.
Okay, just over there.
Yeah, okay, yeah. Light is blinding, sorry.
So you spoke about AI and education, and
yep.
Obviously, well, a lot of people here involved at universities. And what do you think is? Can you elaborate more on that, on the role of AI in education? Because what I'm thinking is happening after COVID, especially. Like before COVID, we were all speaking about online teaching and how teaching was going to change. And then what we all realized after COVID, both teachers and students, was that the human connection was what everybody wanted. Even though the students still want to get everything online and maybe... But
I think it's an area that we need to explore, right? But a digital tutor that can actually interact with you and show you things. And for instance, in programming, there's where programming can now be done together with a co-pilot that helps you correct things, that prompts suggestions. With building simulation, I could do something similar, right? So you give somebody one of the existing tools. I'm sure that the people that develop Design Builder, IES, you name them, at the moment, they have tutorials online, which are kind of static YouTube videos that you can follow. You can turn those into something where you can interact with, and you can pilot that with AI and kind of get better feedback in there. How much of that we want to completely rely on just doing that and there's no more critical voice, that is the academic's job. And I think one of my jobs as a professor is to enthuse people and kind of show different things and give warning signs. And if I talk about teaching simulation, I kind of give the highlight, say this is the structure, this is what the tool does, and then I rely on the tutorials that online for basically dealing with the cursor and what you put in which field, because I don't find that interesting. A question where that moves and how that fits, but I think AI will change that. So, interesting area.
So we actually don't have time for any more questions, but I'm sure Pieter will be around.
I will be around for a little while. So happy to talk with people over the coffee break.
Yep.
Thank you.
Wonderful. Thanks very much, Pieter.